Hello everyone. So let's continue our discussion on the kinematics. So last time we had discussed acceleration, velocity, and other related matters, kinematics. So this time we will discuss about the graphical interpretations. Okay, so these are the concepts for this part. We have functions of time. So velocity time t is the slope of the position curve at time t. Okay, so this is our position curve. So this is our st curve or position curve. So velocity at any time t is the slope. Okay, is the slope. Velocity at time t is the slope of the position curve. So this is our position curve class. This one. Okay, so velocity is just the slope of the position curve at time t. So we have here v. So this is the tangent line to this curve. So to find the slope here, so this is the velocity. V is just the derivative of s with respect to t, or that is equal to s single dot. Okay, so take note on this class. And the acceleration at time t, acceleration at time t. So acceleration at time t is the slope. So this is also slope of the velocity curve. So this is our velocity curve class, the next curve. Okay, so this is the velocity curve, or we have the vt curve. And the area, so the area under the vt curve, So you see here in our curve, so the area, okay, so this area here. Okay, so this area here under this vt curve. So this is the displacement or the net displacement. So this is the net displacement of the particle during the time interval. Okay, so to calculate s, so we have to use the vt curve, and then we have to make use of this formula. So where this formula coming from? So we have the velocity. So originally this is the main concept here, that velocity is equal to the derivative of position with respect to time. All right, and then cross multiplying dt, so we have v times dt equal to ds. So ds, all right, and then integrating both sides. So integrate both sides, so that is why we have this expression here. Then we can solve for the s. No? S is the difference, no? The area under this vt curve, which is s2 minus s1. All right, so what is S2, what is S1? So if at this point, so referring to this uh, V, so this can be our S1. Then at this point here, so this could be our S2. So the okay, so the limit is, so this is the distance, no? The position. So from this point to this point, the particle is moving from this point to this point. All right. So to find S, which is the net displacement, this is the area under the curve. So we can do that, no, from our lessons in integral calculus. So to find the area under the curve, so we have to do integration. All right. So our limit here for the S is from S1. No, this is the lower limit from S1 to S2. So that's why we have the lower limit. And for the other part, we have the integral of v times dt. So of course, our limit here is the time, no? The velocity with respect to, when you speak of velocity, is that is ds over dt. So we use the time as the lower limit t1 and upper limit t2. Okay, so substituting in this formula, doing the integration, then we get this S2 minus S1 equal to the area under the VT curve. So this is our VT curve. Oh, this is our VT curve. Okay, then the area under the AT curve. So what is that area under the AT curve? So area under the AT curve, so during the interval T1 to T2, is the net change of velocity. So this is the net change of velocity. So you can find the velocity, no, using the acceleration AT curve. Okay, so this is our AT curve, acceleration versus time curve. Okay, so to find the net velocity, so we have to use the formula that acceleration is equal to the derivative of the velocity, okay, with respect to time, and then you cross multiply. So we have a times dt equal to dv, and then after that we integrate both sides. So integrating both sides, okay, so integrating both sides, and we have here the limit for v. Our limit is in terms of v1, no? The lower limit is v1, upper limit is v2. Then for our dt, so when you integrate dt, that is equal to t, so the limit is from t1 to t2. So this one, from t1 to t2. Okay, and then after evaluating this integral, so we have this result, because integral of dv is v, so limit of lower limit v1, upper limit v2, so you subtract, no, v2 minus v1 equal to, so whatever is the result here, so that will be the area under the AT curve. So you got the net change in velocity. So you can calculate that using the AT curve. All right. Now functions of position. So the area under AS curve. So we rewrite the, or redraw the, or we show again the AT curve here. So this is our AT curve. So the area under the, sorry, this is ES curve, not AT class, but ES curve. So we have area, sorry, acceleration and displacement. So this is ES curve. So the area under ES curve between positions S1 and S2 is 1/2 the difference of the squared of velocities of the particle at 2 points. Okay, this is 1/2 of the difference of the squared velocities of the particle at 2 points. Okay, so assuming at this point here, okay, and at this point. So area under E is curved. Okay, so and this is derived, no, from this relationship. Again, this is taken from the formula that we have a while ago, no, from this one. Okay, so we have to make use of this formula or this one. Okay, so from that, then we integrate both sides. So so just for reference, no, we have acceleration. Acceleration is equal to v times dv over ds. Alright, so after that you cross multiply, so you have a ds then equal to v dv. Alright, then integrating both sides, so integrate this one, so we have this. Okay, or so after evaluating the integral, so we come up with this 1/2, because integral of v dv is v squared over 2, or 1/2 v squared, and substitute the limit v2 minus v1. Okay, so you have this 1/2 v2 squared minus v1 squared equal to the area under the S curve. Okay, so take note on this. Then we have here the vs, no, vs curve. So a line, if we draw a line, so if you're going to draw a line perpendicular to the slope of vs, so draw a perpendicular line to the slope of vs. So what is the slope of vs? So this is our vs, class. Okay, this is our vs curve, and this is the tangent line. Okay, this one, the tangent line part of this triangle here. Now if you're going to draw a line perpendicular to this slope or tangent line, so we have this line AB. Okay, so line AB, and then if you drop a line from this point of tangency down perpendicular to this s-axis, so we will form a right triangle here. Alright, then from this slope tangent line, we have this triangle. This is the rate of change, no? We have this height here of this triangle, the rate of change of the velocity with respect to distance s. Okay, so because this is v versus s, so this height here varies, no? Depends on where is the velocity. If the particle is moving at this point here, so we have this velocity at this point with respect to s, so we have dv over ds. Okay, and this is 1, and take note, these are similar triangles because the angle here, okay, is just the same as the angle here. Okay, so that's why they are considered as similar triangle. All right, now from the concept of the similar triangle, we have here the line segment CB. This line segment here from C to B, so we have here CB. The bar above means line segment, so the line segment CB divided by this height of this triangle, or the leg of this triangle, which is V. Okay, that is equal to, we are using the principle of a similar triangle, class. So we have dv over ds. Okay, this is the base also. This is the base of the triangle. All right, and then divided by this leg of this triangle. So that's why we have dv over ds divided by 1, so that is still the same. Or we can solve for CV, or the line segment CV, by multiplying both sides by V. So that's why we have here CB equal to V times dV over ds, or V times the derivative of V with respect to S. And that is the acceleration. So that is where this formula is taken from. Okay, this is the graphical interpretation class. A while ago, we just solved this mathematically, but now you have seen how this formula is being derived. Okay, that is the graphical interpretations. So you can see it from the graph, how this, or where this formula coming from. Okay, now we have analytical differentiation. If position is given as a function of time, so we have s equal to, or s as a function of time, so we write it this way. Okay, s as a function of time. Then differentiate once to obtain the velocity as a function of time. So it means that we have the velocity also as a function of time. And now if you are going to differentiate it a second time, then we will get the acceleration as a function of time. So we have a as a function of time. So acceleration as a function of time. All right. So the functions for position, velocity, and acceleration are easily plotted and evaluated at times of interest in order to obtain desired information. So if position is not given as a function of time, it must be determined by successive integrations of the acceleration, which is determined by the forces which act on the particle. All right. Now we have here analytical integration. So we have four cases here. For case number one, we have constant acceleration. Okay, so our acceleration is constant. So this is our case number one. So constant acceleration, case number one. Okay, so in this case, at time t, now at time t equal to t sub 0 equal to 0. So initial time t sub 0. So the particle has a velocity equal to v sub 0, or initial velocity, and is at a position, or position s equal to s sub 0. Okay, now if we're going to substitute into this equation, which we have derived a while ago, and integrate once to obtain the velocity as a function of time, so we got this. Okay, so from here we integrate both sides. Now the limit for this one, so we just rearrange this one class. So this is actually, this one is taken from this one, and then we integrate both sides, and then we rearrange the position. So this one is on the right side, now we put it on the left side. Okay, and then integrating, so the limit here, the lower limit is the initial velocity v sub 0, final velocity as v, and we have here the initial time as 0, then t for the final time. So integrating, so we got here the integral of dv is equal to v, then the limit is v sub 0 to v, then substituting the limit, so we got here above this we still have 1 line here, so this is supposedly v minus v sub 0. Okay, so this is the result class after evaluating this, equal to a times, so substitute the limit, so t minus 0. Okay, so after that you transpose this v sub 0 to the right side, so this is it. Okay, then a times t, so we have a times 0, so 0, so therefore we have this v final velocity is equal to initial velocity plus the acceleration times time. Okay, so this is a very important formula class that we need to understand and also make use of it later on in our coming examples. Then if you're going to substitute, so this result we are going to substitute to the other equation, no, from here. So we have here another equation that v dt equal to ds. Then when you integrate both sides, so rearranging, we write v dt first. Then our v is this one. Okay, so substituting the value of v for in this equation, then integrate, so we got this one. All right. So after integration, so by the way, the limit here is s sub 0 and s. So when you integrate, so after the integration, we will get this s minus s sub 0, okay, equal to, so integral of this, so you distribute dt and also this integral sign here, then you distribute this one and multiply, okay, and integrate individually, so you got v sub, then this one, so we have v sub 0 times t. Okay, so v sub 0 times dt, then integrate. So integral v sub 0 is a constant, integral of dt is t. So that's why we have v sub 0 t. Then plus, we have here a t dt. So integrate that one. A is constant, so isolate a. Then integral of t is t squared over 2. So integral of t dt is t squared over 2. So that's why we have here 1/2. Okay, so we have 1/2 a times t squared. Okay, and then transpose this a sub 0. So that's why we come up this formula. Okay, so this is our second formula class. Very important formula that we need to remember and understand. Then substitute this result here in our next equation, and then integrate. Okay, so this is our next equation class. A ds equal to v times dv over ds. So substituting the value of s here. Okay. So integral. We have, okay, so a, then isolate the a, we interchange the position class, so we have a integral of ds, limit from s sub 0 to s. Then we have here v dv, so v dv, so integrating, so v, that would be v squared, right? This would be v squared over 2. Okay, v squared over 2. All right, so v squared, substitute, we have v squared over 2, and then it will look like this. So we have, when you integrate this one, so we have v squared over 2. Okay, and the limit is from v sub 0 to v. So this is equivalent to v squared minus v sub 0 squared. And then you have multiply this by 1/2. 1/2 is the common, or divide this by 2. So 1/2. Okay. Sorry, it's not clear. Let me do it again. So after this part, when you integrate, so we have here, so isolate 1/2 because that's a constant, and then substituting the limit, so we have v squared, this is upper limit, you square that one, so v squared minus lower limit is v sub 0, so v sub 0 squared. Okay, so this is it now, and then you multiply both sides by 2 just to eliminate this fraction here. So this becomes, when you multiply both sides by 2, so this becomes v squared minus v sub 0 squared equal to, so we have 1/2 times, okay, so using this one, and the value for s, no? When you substitute, we have s here. Then when you manipulate, so you have 2as because you multiply this by 2. So okay, so from we have substitute ads, meaning this result here, we are going to substitute it here. So on the left side, this is what we have done on the left side. And the right side, so after you integrate this one, a, so this will be a times s, because integral of ds, no, the integral of ds is equal to s. Okay, equal to s, and the limit is, we have s sub 0, then s. So substituting the limit, so this would be uh, s sub 0, and this is s. So s minus s sub 0. Okay, and then we have here a, no, because we have a here, so you still have to multiply this by a. So this is times a. Okay, so this is our equivalent. So let's make it clear. So this is times a. Okay, then after that you multiply both sides by 2, so that's why you have 2 here. So that's why we have here 2as. Alright, so this is now the third equation. So this is supposedly 2a times s minus s sub 0. Okay, and then transposing v sub 0 squared, and that's why we have it in this equation. Okay, now case 2. So case 2 is, we have acceleration as a function of time. So our acceleration here, a, is a function of time. Okay, so we have to make use this relationship. So now we are going to again assume that at t equal to t sub 0 equal to 0. So the particle has a velocity of v equal to v sub 0 and is at the position of s equal to a sub 0. Then substitute it to this equation, right? So substituting in this equation, and then you integrate both sides, rearrange the position. We put this a dt here on the right side, then dv on the left side, and then integrate both sides. So for dv, the limit is from initial velocity v sub 0 to final velocity v, or to an instantaneous velocity v. Then equal to the integral of a. A is function of time, so we have function of time dt, so limit 0 to t. Or when you evaluate that one, so this will be, no, the upper part here, this will be derivative of dv is v, then substituting the limit, so you have here v minus v sub 0. Okay, then equal to, you have integral of this, so you just copy that one. Okay, then after that you transpose this to the other side. So we have integral of 0 to t, then ft dt. Okay, then after simplifying, so we got this formula, class. So remember this because this is a very important formula as well. Okay, now substitute the previous result, meaning this result here. So we are going to substitute it here in this equation. Okay, I mean, so you have your v equal to v sub 0 plus the integral of this one. Then you have here the equation below. From here, we integrate both sides. So on the left side, the limit is from s sub 0 to s equal to integral of v dt, but we have an equivalent, no? We have integral of v dt. So from here, you can solve for s, no? The integral of this. This is supposed to be, so we still have here, when you integrate this part here, class, so the integral of ds limit s sub 0 to s, so this is equal to s, so the limit is s sub 0 and s, then you substitute the limit, so we have upper limit s minus the lower limit s sub 0. So s minus s sub 0. Okay, then you transpose that to the other side, so that's why, so supposedly here we have s minus s sub 0 equal to, so v, so v uh, integral of 0 to t, we have v dt. Okay, then substituting, transposing this part here, so we have s equal to s sub 0 plus this one, then you can substitute the value here. Okay, so when you substitute the value, your v is equal to this one, so what will happen? Okay, so it means our s here is equal to s sub 0, then plus, so integral of limit from 0 to t, then v, our v is this one, so v sub 0 plus the integral of f dt. So we have the limit here 0 to t. Okay, v sub 0 plus, so this is our s. So if desired, the displacement s can be obtained by direct substitution of a second order. This is a second order differential equation of the form something like this, but this is more difficult, so it's better to stick with this solution, class. Now for case number 3, okay, so this is our case number 3. So acceleration as a function of velocity. So we have a as a function of velocity. So we assume here that at time t, we have t is equal to t sub 0, or t sub 0 is equal to 0. And the particle has a velocity v equal to v sub 0, and is at the position s equal to s sub 0. Okay, now substitute this, or substitute into this equation, e is equal to function of v, where a is equal to the derivative of v with respect to t. Alright, and then we can separate variables and then integrate once to obtain the time as a function of velocity. And we got this t here is equal to the integral of dt, which is equal to the integral of, so our dt here, okay, our dt could be dv over f of v, so that is taken from here. Just manipulate this one, class. Alright, so this could be inverted to obtain velocity as a function of time, which could then be integrated as before, so to obtain position as a function of time, or differentiated to obtain acceleration as a function of time. Then after that, you substitute it into this equation, then separate variables and integrate once to obtain the relationship between the position and velocity. Okay, and it is given in this equation, the integral of v dv over f sub v, limit from v sub 0 to v, equal to the integral of ds, limit from s sub 0 to s. Or we can solve for s here. S is equal to, of course, when you substitute the limit, so you have two s here, s and s sub 0, then you transpose it to the other side. So this becomes positive, then add it to this. Okay? So another important formula, class, that you need to remember. So for the time, okay. So for case number 4, so case number 4, our acceleration is a function of position. Okay, case number 4, acceleration a function of position. So a equal to f of s. So again, we use the same assumption here. T equal to t sub 0 equal to 0, and velocity equal to v sub 0, and the position is equal to s equal to s sub 0. Then substitute into this equation. Okay, and then you integrate both sides, then apply this technique in integration, separate variables, and then you have to integrate once to obtain the relationship between position and velocity. Okay, so from here, so we have v dv, you cross multiply ds here, so we have fs ds. So integrating both sides, we have the limit here for v sub 0 to v, and s, the limit of s is s sub 0 to s. Or, so substituting, so we got this new formula. So this is our new formula, class, that we need to understand and remember. Okay, now solve for the velocity as a function of position, or v equal to g sub x. So velocity as a function of s, position. And substitute into this for the velocity. So you take the derivative of this with respect to time and you substitute it here. Then separate variables and integrate once to obtain the time as a function of position. Okay, so we got here the time equal to the integral of ds over g sub s. Okay, class, so this is just integral, so I will not give the details on this. So it's assumed that you have passed your integral calculus. Okay, so this function can be inverted to obtain position as a function of time, differentiated once to obtain velocity as a function of time, and differentiated a second time to obtain acceleration as a function of time. Okay, so now we go to the problem statement. But I think this is already a very long class, very long video, so I need to stop up to this point here, and we'll have another video to illustrate how to solve problems using these concepts, these formulas. All right, so thank you very much, and see you in the next video. So bye.